Okay, let me start with some motivation to study free boundary minimal hypersurfaces. So consider general Riemannian manifold with boundary, and sigma is some compact submanifold such that the intersection of sigma with the boundary of the ambient space is the boundary of sigma itself. So I want to consider the variational problem of find critical points of the volume functional. So in my case, I will consider only variations of the submanifold such that the boundary of the submanifolds on the variation are also inside the boundary of the ambient space. So a picture will be something like that. Here M is the ball, the boundary is the circle. So my initial submanifold is represented by this curve in blue, and the curve in red represents some other submanifold on the variation, and here the green arrows represent the variational vector field, and you can see that the boundary of the submanifolds are inside the boundary of the ambient space. So I want to consider critical points of the volume under these conditions. So if you look to the first variation of area or volume, okay, let X denote the variational vector field, and this condition about the boundary of the submanifolds in the variation says that X is tangent to the boundary of M. So by the first variation of area, we'll have the following. And if you suppose that the first derivative of the volume is 0 for all such variations, we obtain that the submanifold is minimal, so the mean curvature vector vanishes, and sigma is orthogonal to the boundary of M along its all boundary. So there's a variational motivation to study these objects. So another motivation, which is from an analytical problem, and which is very specific to the case of the Euclidean ball, is the following. Here sigma is some compact manifold with boundary and endowed with some Riemannian metric. So we want to consider the following operator, which takes functions on the boundary to functions on the boundary. So first, for a function on the boundary, I can consider the harmonic extension. Then, with respect to the unity chord normal, which is outward pointing, I can consider the derivative of the harmonic extension. Okay, so this defines a non-negative self-adjoint operator, and we can see it has discrete spectrum, which satisfies the following. The very first eigenvalue I denote by sigma 0 is actually 0, and it is simple, and the eigenfunctions are the constant functions. So I will denote by sigma 1 the first non-zero eigenvalue, and we know it is a no decrease sequence going to infinity. Okay, so what is the relationship of this problem with free boundary minimal submanifolds? observation by Fraser and Chen. Let me sigma be an immersed submanifold of the Euclidean ball. For simplicity, we can suppose it is compact, and suppose that the intersection of sigma with the sphere, which is the boundary of the ball, is the boundary of sigma. So sigma is a free boundary minimal submanifold if only if the coordinate functions of Rn, when restricted to sigma, these functions are eigenfunctions of my operator L with eigenvalue 1. Okay, so this is a important characterization. So now let's move to some basic examples of free boundary minimal hypersurface in the ball. So first we have the equatorial disks, which are the simplest examples of such objects. So the idea is that I take any hyperplane through the origin. Okay, for me the ball is always the Euclidean ball with radius 1 and center of the origin. Okay, so take any plane through the origin, and the intersection of this hyperplane with the ball is a free boundary minimal hypersurface. So is a result by Nietzsche that every free boundary minimal disk on the three-dimensional Euclidean ball is an equatorial disk. So have a unicity result, which highlights the importance of the examples at least in dimension 3. Okay, the next examples are the critical catenoid in dimension. So this is the unique up to Congress free boundary minimal hypersurface of a revolution in the Euclidean ball. So this is homeomorph to a product of a closed interval with the sphere of dimension n-1. In particular, if n is equal to 2, then we are inside the Euclidean tree ball. So this is homeomorph to annulus. So here it is a sketch of the critical catenoid on dimension 3. The ball has dimension 3. So this is a picture by Mario Schulz. He was kind enough to allow me to use some of his pictures on my talk. And one observation is that these examples have a lot of symmetries. And one can think about other examples with a large group of symmetries. So in this direction, Fradin, Gullian, and McGrath, they construct examples which are invariant under groups of cohomogeneity 1 or 2. So these three classes are the most basic examples of free boundary minimal surface in some sense. So let's move to other examples. So our first class of examples is obtained by the so-called eigenvalue shape optimization problem. So here we restrict to the case n equals 2, so the ball has dimension 3. So the idea is take the first non-zero on any compact surface, fix a compact surface, and I can consider all the remaining metrics on this surface. So consider the following functional. I multiply the first non-zero Dirichlet-Neumann eigenvalue by the length of the boundary with respect to the metric. So the idea is to maximize that. It is a classical result that this is actually bounded above just in terms of the topology of sigma. So Fraser and Shen, they obtain a characterization of the maximizers of this problem is free boundary minimal immersions in some balls. So if a maximizer exists, so it is obtained as a free boundary minimal immersion in some ball, possibly with branch points. And at first we don't know what is the dimension of the ball. And also they obtain a partial construction of examples on the three-dimensional ball, which have genus 0 and any number of boundary components. On the case of the two boundary components, they were able to prove that this is in fact the critical catenoid. And of course it is easy to prove that on the case the number of boundary components is 1, this is the equatorial disk. So Matisse and Petridis, they completed the construction of this previous surface of genus 0 and any number of boundary components. Actually, they proved a more general result that this problem always has a maximizer, but maybe if the topology, the genus is not 0, the ball has dimension greater than 3. Okay. But at least if the genus is 0, we know that we realize the surface inside the Euclidean tree space. And also we have this very interesting result by Karpuk and Stern. They prove that these previous surfaces, they converge to the boundary of the ball, S2, as the number of boundary components goes to infinity. Also, Capulis and Zhou construct some examples of free boundary minimal surface in the ball accumulating on the sphere, but it's not clear if these are the same surfaces. So a sketch of a picture of this surface would be something like that. As the number of boundary components increase, these boundary components are becoming in some sense small, and the yellow part is become closer and closer to the sphere. Okay, and we have more examples, and basically people have used two techniques to obtain these examples. Is a GUI technique based on PDEs, and min-max theory for the area functional is the other approach. So here again, the examples are on the case n equals 2. So inside the Euclidean tree ball. And now we'll denote gamma, the genus of the surface, and k, the number of boundary components. So first, Folha, Pacá, and Zolotareva, using the gluing technique, they construct examples also with genus 0 and a large number of boundary components. And so the idea is take a doubling of the equatorial disk and try to glue these two copies. And also they can replace the genus from 0 to 1. So a sketch will be something like that. On the left we have the case of genus 0, and here we have 8 boundary components, and on the right we have genus 1 and 5 boundary components. Okay. So next, Kitove using the Mimax technique and Capoeira using gluing. They construct examples with some particular symmetries. Then Capoeira and Wiggle construct examples with high genus and connected boundary. And the idea is now, instead of doubling the equatorial disk, so they consider 3 cups of the equatorial disk and try to join them in such a way that now the boundary is connected. And then Carlotto, Franz, and Schulz, using the Mimax technique, they actually proved that for any genus there is a free boundary minimal surface in the Euclidean tree ball with boundary connected boundary. Also using, so in all these previous constructions using Mimax, people have used equivariant Mimax, so version of Mimax technique which always takes on account symmetries. But using the Almgren-Pitts version, Sun, Wang, and Zhu prove that there is a sequence of free boundary minimal surface on the Euclidean tree ball such that the areas are going to infinity, and they observe that they can use that to see that the surfaces are actually different from all the previous families. And finally, we have examples with 3 boundary components and large genus. First by Kitove using the Mimax, the equivariant Mimax. Then Capoeira using GUI. And finally, Carlotto, Schulz, and Wiggle. They studied this problem and found that there are 2 families of this type of surface which have the same topology, the same symmetry group, but they are actually different. So the picture will be something like that. On the first family, on the left, this surface kind of resembles the Hoffman-Costa mix minimal surface on R3. And Carlotto, Schulz, and Wiggle found this other family on the right. Okay, so the theory developed very quickly, and now we have this plenty of examples of these objects. So now I'll move to the main result, which is the so-called two-piece property. So before I start talking about two-piece property, let me observe that there is an analogy between closed and minimal hypersurface on the round sphere and the compact free boundary minimal hypersurface on the Euclidean ball of the same dimension as the sphere. So this analogy has been guiding the researchers on the subject, and there are a lot of results which can be seen. Results about the free boundary minimal hypersurface on the ball, which can be seen as an analog of results for closed minimal hypersurface in the sphere. So let me mention this beautiful result by Ross, which says the following. Suppose that I have a closed embedded minimal surface on the Euclidean um, suppose I have a closed embedded minimal surface on the round 3 sphere, and take any equatorial spheres. So either sigma is equal to this sphere, or the sphere divides sigma in exactly two connected components. So this kind of says that the embedding cannot be very complicated, right? So this result is very beautiful, but also is very important because it gives evidence to a conjecture to Yao. So the conjecture is on all dimensions. Suppose that I have a embedded closed minimal hypersurface on the round sphere of dimension n plus 1, then the first non-zero Laplacian eigenvalue of sigma is equal to n. So why I say that this gives evidence, the two-piece property gives evidence to the conjecture. The idea is that I can combine the statement of the conjecture with the Courant nodal domain to prove the two-piece property. So the idea is suppose that the two-piece property is not true. So, for example, I can consider coordinate functions. So if I have some sphere that divides the surface in more than 2 components, so this sphere is related to some hyperplane in R4. So I can construct a function with respect to the normal vector, which is a kind of a coordinate function. And this function is harmonic. And I can use the Courant nodal domain together with the Yale's conjecture to find a contradiction. Okay. So inspired by that, we thought about an analog of the two-piece property for free boundary minimal hypersurface on the ball. So first, we proved the case of the three-dimensional ball in 2019. Then 2 years later, we proved the case on n dimension. So the statement is the following. Suppose that M is a free boundary minimal hypersurface on the ball, which is compact and embedded. So for any equatorial disk, either M is this disk or the disk divides M in exactly 2 components. And read by the statement, we can see the resemblance to the two-piece property on the sphere, but the analogy goes further, and there is a conjecture by Fraser and Lee, which is the analog of Yale's conjecture on all setting. So it says the following. If I have a free boundary minimal hypersurface on the Euclidean ball, which is compact embedded, then the first non-zero Steklov eigenvalue is equal to n over 2. And again, the idea is that the statement of this conjecture together with the Courant nodal domain implies the two-piece property. And here the Courant nodal domain is the version for the Steklov eigenvalue problem. Okay, and the idea is the same as before. We apply that for some coordinate function associated to a hyperplane. And so the statement of the conjecture together with the coronal domain implies the two-piece property. Okay, let me mention that the Viver and Tran independent prove that the conjecture is true if the ball has dimension 3 and the Morse index of the surface is equal to 4, which is the index of the critical catenoid. So now I move to a sketch of the proof of the two-piece property. So first, if the hypersurface M is an equatorial disk, then the result is a consequence of a basic Euclidean geometry. So I can start supposing that M is not an equatorial disk. And I will suppose by contradiction that M minus D has more than two components. So the key to prove the statement is consider a kind of partial free boundary problem, which I will explain now. So let M1 be any connected component of the M minus the disk, and this has some boundary gamma. So it is a result by phrasing we that the complement of M inside the ball is exactly two open regions with compact closure. So here in my picture, think of the hypersurface is the catenoid. So the two domains are the inside of the catenoid, which is on gray color, and the other domain is the outside, which is represented on the green color. Okay, so if I think now of my hyperplane, which gives the disk D is being this represented in red, so my curve, actually my submanifold gamma, is represented here by this red curve. Okay, and the idea is to consider some partially free boundary problem with respect to this red curve. Okay, what is the idea? So I can consider a closed curve now if I join the ends of the two components of the red curve by first by a blue curve up, then a blue curve down. So I have now a closed curve with two parts, one part inside the interior of the ball and two parts inside the sphere, which is the boundary of the ball. So in the case of high dimensions, this will be submanifolds of dimension n minus 1. So what is the idea? I keep the submanifold in red fixed, and I allow the submanifold in blue to vary inside the sphere. And I will consider all the submanifolds, all the hypersurface which have as the boundary a submanifold like that, such that the fixed part is the red part and the free part is on the sphere, the free part of the boundary. So the idea is try to minimize the volume on this class. So to consider this problem, this generality, actually we need to use some results of geometric measure theory. So actually we are going to minimize on the class of rectifiable integer multiplicity rectifiable currents. If you don't know what a current is, just think it's a kind of generalized submanifold which has some control singularities. And here we have to minimize the mass, but the mass on the case of submanifolds is actually the volume. Okay, so a classical result on GMT says that there is a minimizer for the mass on this class, but first this can be a current, and we don't know if the current is obtained by some smooth submanifold. We would like that to be true. First thing we have to prove, we prove that on the papers, is that it's a maximum principle. Consider the support of the current, and then we prove that either just to be clear, I'm minimizing first inside one of the domains, right? Let's say I minimize inside the domain in gray. Let's say this is W. So either the surface, the hypersurface, is entirely contained on the boundary of the domain, or it is inside except by his own boundary. That is, the intersection of sigma with the boundary of the domain is the boundary of sigma itself. So this maximum principle is important to obtain irregularity. Okay. The irregularity on the first case, sigma is inside the boundary of W. I already know that the boundary of W is a smooth hypersurface, but on the other case I have to try to prove regularity using GMT. So what regularity theory says? So first, there are a lot of type of singularities, and there are two particular cases of singularity we have to consider are the corners. So a corner is a point where the fixed boundary meets the free boundary. So here on the picture, a point where the blue curve meets the red curve. And there is also this so-called K-prong singularities, which is the case where the hyperplane is tangent to my hypersurface M. By the maximum principle, I know that the hypersurface cannot be on only one side of this plane, so they are components on the two sides, so the picture will be something like that. And on the first case, the tangent point is on the interior, and on the other three cases, the intersection is at the boundary. So if I have a situation like that, here the picture is only on dimension 2, but we have a similar description on all the dimensions. So if this happens, I'll add my submanifold in red has some singularities, right? So I have to take care of these two types of singularities. And the regularity theory says that there is a set S1 such that away from S1 and the coordinates and the k-prong singularities, the support of the current is actually a smooth submanifold, a smooth hypersurface. And depending on the dimension, I can say actually that the set S1 is empty, at least if n is at most 6. If n is 7, I know that it is a discrete set, and in general, for n greater than 7, I can only say that the set has codimension 7. So we have some singularities, but they are controlled. Perhaps we will have singularities, but they are controlled. But let me just mention that on the first paper, on dimension 3, we proved that the current on the situation is actually regular the coordinates. We don't actually need that to prove the two-piece property. We will see that. However, there was an approach for this problem by Gruder and Simon, and we followed this approach and completed the proof of the result. So what is the step 2? So I obtained this generalized hypersurface, minimize the area for the problem, and I want to actually prove that this object is containing some equatorial disk. So remember, I have two parts of the boundary, one a fixed part on the interior and a free boundary on the sphere. And since I obtained the surface, the hypersurface by minimization, I consider the second variation of volume. We can prove that the so-called stability inequality holds. So for n function on H1, such that the function vanishes on the fixed part of the boundary, this inequality holds. So what is the idea to prove now that the submanifold is contained in some equatorial disk? The idea is to prove that the submanifold is totally geodesic, and then this followed by a classical result in differential geometry. So how do I prove that? I want to use this inequality. So the idea is to choose some function such that I can get rid of the first term, which have the Laplacian, and the term on the boundary. So these functions, which are of the type fx is x product with some fixed vector, I can consider is a unit vector. So they are spectral, they are special, they are kind of coordinate functions, and I can see since the surface is the hypersurface is minimal, the Laplacian of such a function is 0. So I get rid of the first term, And by the free boundary condition, I can get rid of the boundary term. And this will give me that I have just the term with second fundamental form here, and since I have a minus outside the integral, the right hand side with less than equal to 0, but the stability inequality says that is greater than or equal than 0, and I can use that to prove that IP surface is totally geodesic. Then by classical differential geometry, a classical result says that in this case the IP surface is contained on an hyperplane. So the problem here is that maybe sigma has some singularities. So in order to take care of the singularities, I have to consider perturbations of this type of functions. I can consider some special cutoff function will support are small neighborhoods of the singular set, and I start to decrease to the size, let's say, of these neighborhoods as epsilon goes to 0, and I can see that by some calculations that the previous argument works on the limit, and I can conclude what I want. Okay, I know that the IP surface is containing some equatorial disk, but I actually want to conclude that it is contained on my original equatorial disk, the disk D I started with. So what is the idea? First, we want to prove that the case sigma contained on the boundary of my domain V cannot happen. This is because of the maximum principle. I know that sigma is containing some disk, but the boundary of V is my original IP surface, and I started the proof. Suppose that it is not an equatorial disk. Now I can prove that each component which is now bounded by the n-1 dimension equatorial disk is necessarily contained in D. So the idea for doing that is just using the Euclidean geometry of disks on the Euclidean ball. And the first step is that actually prove that there is no such component which is bounded by n-1 dimensional equatorial disk. For that, I need 3 versions of the maximum principle. I need the maximum principle at the interior, the maximum principle at the boundary, and maximum principle at the coordinates. Remember that my IP surface has coordinates. And there is actually a version available for maximum principle on the coordinates by Serrin. And the idea is that suppose this is true, and I can consider rotations of this equatorial disk, and I want to see a first point of contact to obtain a contradiction. And so that's why I need to use the maximum principle, right? And the first point of contact, I don't know if it happens at the interior, the boundary, or the coordinates. That's why I need the 3 versions. So okay, what is the idea now? Let's come back to the picture. So suppose I did the minimization process on the gray domain. So on this case, my surface will be something like that, like this piece on gray of the equatorial disk. But then I can consider the same process on the other domain, and I construct another hypersurface, sigma prime, and I actually applying the same arguments as before. I conclude that the union of the two hypersurfaces are the disks D. In particular, the intersection of M with D is just my fixed boundary of the problem I was considering. So this implies that the other components of M minus the disks have no fixed boundary, and this is a contradiction. I can obtain a contradiction using the maximum principle. So here's the picture when I do the minimization problem on the gray domain, I obtain this gray part of the disk, and when I do on the other domain, I obtain the green part. So this finished the proof by contradiction. And by using the same techniques, we can prove the following result, which is also a generalization of a result by Haas. It says the following: consider a region which is compactly connected inside the ball, such that the intersection of the boundary of the region with the interior of the ball is smooth, mean convex, and intersects the sphere orthogonally. Then we can prove that this region, if this region contains a n-1 dimensional equatorial disk, which is homologically trivial on the inside the region, then the region is a half ball. And the idea is to use the arguments is on step 1, 2, and 3. I do the minimization problem inside my region, and I use step 2 and 3 to prove that the hypersurface is actually containing an equatorial disk, and obtain a contradiction using the maximum principle. So finally, let me finish with some applications to the unicity problem for the critical catenoid. So it is also a conjecture by Fraser and Lee that every embedded free boundary minimal annulus on the Euclidean tree ball is congruent to the critical catenoid. So this is analog of the Lawson conjecture for embedded minimal tori on the Euclidean tree sphere, which we know now is true due to Brendel. So we have some partial results in this direction. For example, Fraser and Shen prove that for the case that the first Stekelov eigenvalue of the surface is 1. And McGrath proved that for if supposing that the surface is symmetric with respect to the coordinate planes. Also, Ambrosio and Nunes, they proved a more general result, but on the particular case of an annulus, if this inequality is true, then the surface has to be the critical catenoid. So here n is normal vector field, unity normal vector field to the surface on the Euclidean space. So it follows from the result that actually if the surface is annulus, this is actually 2, and it is the critical catenoid. So in 2020, using my graph, proved that embedded free boundary annulus is invariant by the antipodal map, so is a hypothesis of symmetry, but different from the previous hypothesis by my graph. Then sigma is congruent to the critical catenoid. And a key part of the proof of this result is the two-piece property. On the paper, they also proved the result for other types of surface with some different symmetries. And in 2021, Cell proved the following, again using the two-piece property, that if I have a free boundary embedded minimal annulus on the ball, and now instead of consider symmetries on the whole surface, we have to consider only symmetries on the boundary. So if the boundary is invariant either under the antipodal map or under refraction through two coordinate planes, then we can obtain that it is actually congruent to the critical catenoid. So the two-piece property was actually useful to prove some results in the theory. Okay, thank you very much for your attention.